In the continuation of the previous problem, we now want to add one more constraint. Our feasible region has already been reduced to 2 points. The 2 points that we have here may be affected by this new constraint that we're going to add, which is suppose also that each serving of dates takes up 2 cubic inches of packaging and that each serving of apricots takes up 3 cubic inches of packaging. The company can process at most 78 cubic inches per box. Does the optimal number of servings of each change? Okay, so we know that for each serving of apricots, it'll take up 3 cubic inches of packaging. So that'll be 3x. That'll give us the total number of cubic inches taken up by apricots. For dates, that's going to be 2y. And we want that to be less than or equal to 78, because that's the most we can possibly package. So what's that going to look like as a constraint? Well, we'll have 2y is less than or equal to negative 3x plus 78. And we have y is less than or equal to negative 3 halves, which is 1.5x, plus 78 divided by 2 will be 39, I believe. And so now we can plot that. Well, what's that going to look like? Well, it's going to have an intercept at 39, which is somewhere way up here, and then it's going to have a decreasing slope that's going to go in this direction. So the question is, will it intrude on our current feasible region, which is this almost parallelogram type shape here? Well, let's see. We'll add that constraint in, and if it doesn't encroach on our feasible region, then we don't have to consider it. It should not change anything. So I'll type that in, plus 39, and I'll graph it, and there it is. Oh, and you know what? It turns out that in fact this does not affect our feasible region. So the answer is no. Based on all the previous constraints, 5, 10 is still our best option.